Welcome back to the deep dive. Today, we are strapping in and really getting into the driver's seat of the future.
We really are.
We're analyzing a massive strategic blueprint that, honestly, it feels like it's defining a whole generation of industrial transformation.
It is. We're looking at a very high-level roadmap. It's called the Energy Saving Technology Cluster Roadmap, and it projects the future of mobility all the way out to the year 2040.
And just to be clear for everyone listening, this isn't some, collection of fluffy trend reports.
No, not at all. Think of this as a comprehensive analytical blueprint, the kind that's designed to guide, well, enormous industrial investment.
So our mission today is what, exactly?
Our mission is to really dissect its complete vision, the goals, and I think most importantly, the really precise, highly ambitious milestones they've set for 2030, 2035, and then 2040.
So we're essentially delivering the definitive strategic overview of this whole transformation.
Exactly.
When you first look at this blueprint, the thing that immediately jumps out is just the sheer magnitude of the change being planned.
I mean, this isn't about tweaking an engine. The sources are calling this and I'm quoting here, a century-long revolution.
It's a huge claim, but it's backed up. Specifically, they frame it as an ecological revolution.
Right, and it's being powered by these two absolutely massive interconnected engines of change.
And these two forces, they're not just running in parallel, they're synergistic. They're driving convergence across sectors that, have traditionally been completely separate.
Okay, so let's break them down. Engine number one.
That's carbon neutrality.
The big one.
The big one. That's the ultimate target, the North Star for the entire green transformation, and really the redesign of our whole energy system.
And engine number two is artificial intelligence, AI.
Right. And AI provides let's call it the disruptive mechanism. It's what's shifting the entire innovation paradigm away from that slow, incremental improvement model that we saw in the 20th century.
You mean like making an engine 1% more efficient every year? Exactly that. We're moving away from that and into an era that's really defined by what the roadmap calls emergent breakthroughs.
And I guess when you fuse those two engines, carbon neutrality and AI, that's when the magic happens. The fundamental identity of the car just completely changes.
It's a radical alteration.
Yeah.
It stops being just a simple, mechanical transport tool that gets you from A to B.
And it becomes
It fundamentally evolves into a mobile intelligent terminal.
a mobile intelligent terminal.
It becomes a complex, high-value asset that's deeply integrated into smart cities and, maybe even more critically, into our regional energy networks.
Okay, that's a huge concept to unpack. Let's start with the AI piece. Where do we begin with decoding this new core operating system?
Well, if we start with AI, the message in these documents is pretty unambiguous. AI is not just a feature you can tick on an options list.
It's not like heated seats.
Definitely not. It is the new core operating system of the entire vehicle. This transformation is what turns the car into what the documents are terming an embodied AI.
Embodied AI. That phrasing suggests a real psychological leap, doesn't it? We're not just talking about a voice assistant that, plays a song for you.
No, we're talking about a perceptive, learning, proactive partner.
A partner. Okay, so let's unpack how that capability sort of filters through the entire value chain. Where's the first place we see it? R&D.
R&D is where it makes the earliest and maybe the most profound impact. We're moving away from that expensive, laborious, searching for a needle in a haystack R&D process.
You mean physically building and testing thousands of prototypes?
Exactly. We're now seeing the implementation of what's called AI for Science, or AI4S.
And how does AI for science actually help achieve something tangible, like, say, carbon neutrality?
Okay, great question. So consider the race for better power batteries. That's absolutely central to the whole carbon transition, right?
Of course.
Traditionally, developing new materials for those batteries meant physically creating and testing them in a lab over months, sometimes years.
A very slow manual process.
Very slow. Now, AI for Science allows the system to simulate and compute millions of material combinations and structures, all virtually. It can predict performance, stability, failure points, all without ever mixing a single chemical.
So AI is basically short-circuiting the entire materials discovery process.
That's the perfect way to put it. The roadmap explicitly notes that this virtual testing is leading to exponential leaps in efficiency.
Wow.
It's allowing us to discover new combinations for catalysts, for battery anodes and cathodes in a tiny fraction of the time, We're moving from slow, sequential steps to these emergent breakthroughs we mentioned.
So it's an acceleration engine for the other engine, for carbon neutrality.
It's a fascinating symbiotic relationship. They feed each other.
Okay, let's shift from the lab to the product itself. Smart driving. How does AI change the fundamental logic of how a car makes decisions on the road?
The big shift in smart driving is the creation of what they're calling data closed-loop self-evolution systems.
That's a mouthful. What does it mean in practice?
Well, in the past, autonomous driving relied on thousands and thousands of lines of manually written rules, like, if this happens, then do that. Logic trees trying to anticipate every possible scenario.
Which sounds incredibly brittle and slow to update.
It was. If a new situation came up, a human engineer had to go in and literally update the rule book.
So what's the new way?
Now, vehicles collect vast amounts of real-world driving data. Often this is done in a shadow mode where the AI is driving alongside a human, but not actually intervening.
So it's learning by watching.
It's learning by watching. And all that data feeds back into these massive AI models. This allows the vehicle to continuously learn, iterate, and evolve its own driving decisions. It gets smarter with every mile driven by the entire fleet.
And the system is essentially training itself.
Precisely. And that training loop gets accelerated dramatically by generative AI. It can create high-value virtual scenarios, a super rare accident reconstruction, for example, or a weird traffic situation, and it can stress test the algorithm thousands of times.
So it creates this massive pool of real plus synthetic data.
Exactly. And that whole process, from data collection to automatic labeling, training, verification, and then deploying it over the air, that forms the self-evolution system. It leads to a kind of environmental modeling that's much closer to human intuition.
This is where that embodied AI concept really starts to feel different for the consumer, I think, in the smart cockpit. The blueprint highlights a leap from just passive command execution to genuinely active problem solving.
Yes, what they call the cognitive intelligence closed loop.
Okay, let's get into the example they use, the CL4 cockpit experience. Walk us through that.
So the cognitive level 4, or CL, or cockpit, really illustrates the proactive nature of this embodied AI. The car isn't just monitoring the traffic outside, it's also monitoring your internal context.
My internal context, what does that mean? My calendar.
Your calendar, your usual driving habits, your contacts, yes.
Yeah.
So let's say the system detects some abnormal congestion ahead, like a sudden accident. It knows you have a 9 a.m. meeting in your calendar, and it calculates you're going to be late.
Okay, so it sees a conflict coming. What happens next?
It doesn't wait for you to start stressing out and asking for a new route. It acts like a genuine anticipatory partner. It would proactively deliver a suggestion, something like,
What would it say?
"Good morning. I've detected an accident ahead. I've already planned an alternative route that saves you 10 minutes, and I can send a message to your meeting host informing them you'll now be only 5 minutes late. Should I send it now?"
Wow. Okay, just let's pause on that for a second. It anticipates the problem, it calculates the solution, and it offers to execute the social response on my behalf.
Correct.
The idea that my car is managing my schedule and communicating my delays for me, that's a huge psychological shift in what we're willing to delegate to technology.
It moves the relationship from being a tool user to being a genuine partnership. The vehicle is solving problems before they even register as anxiety for the driver.
That's incredible. Okay, let's move outside the car itself. How does AI impact the huge industrial and supply chain side of this ecosystem?
At the industrial level, AI is fused with what are called digital twin systems.
So a virtual replica of the factory?
A virtual replica of a factory, a distribution center, or even the entire geopolitical supply network. The AI uses these twins to autonomously generate optimal production plans and simulate really complex manufacturing scenarios.
And on the supply chain side, what's the big strategic advantage there?
Resilience and cost control. The AI can simulate different strategies under all kinds of volatile geopolitical scenarios, like what if a trade route is disrupted or a key material suddenly becomes scarce?
So it helps companies become more proactive instead of reactive?
Exactly. It enhances the network's resilience. It allows them to pivot their supplier bases or adjust inventory levels proactively, which ensures precise cost control and stability even when the world gets complicated.
Okay, that makes sense. Let's pivot now to that second massive engine you mentioned, carbon neutrality. The blueprint seems to highlight that even though the goal is shared, the actual paths different major markets are taking are surprisingly different.
They're very divergent. And it tells us a lot about global policy philosophy. We're really seeing 3 distinct regulatory approaches.
Okay, what's the first one?
First, you have the EU. They started with a pure zero carbon mandate, which heavily favored battery electric vehicles, or BEVs.
That seems like the most straightforward path, just go all electric. But what were the practical challenges they ran into?
They hit some serious infrastructural bottlenecks, not enough charging networks, for one. And they also got consumer pushback because of the cost and, frankly, the hassle of managing charging logistics.
So the transition wasn't as smooth as they'd hoped.
Slower than expected, yes. So the strategy has had to adapt.
How are they adapting it now?
Well, now they're re-exploring more diversified solutions. This includes things like hydrogen-based zero-carbon fuels and even synthetic fuels. These are really intended to supplement electrification, especially for things like heavy transport and long-haul driving.
So it's less of a single-minded BEV push now?
It's more of a coordinated, multifaceted approach to get to zero carbon, rather than just a monolithic BEV mandate.
Yeah. Okay, so how does that contrast with the U.S. approach, which is heavily influenced by things like the Inflation Reduction Act, the IRA?
The U.S. strategy is, I would say, fundamentally pragmatic and technology neutral. Their focus is really just on achieving the overall emissions reduction targets. They don't dictate how the manufacturers have to get there.
So they set the goal, but not the method.
Exactly. The policies actively encourage and subsidize a whole diversified portfolio.
Right.
BEVs, fuel cell vehicles, plug-in hybrids, even renewable diesel vehicles. It's about promoting maximum options to meet the overall target.
So the U.S. is prioritizing results and market forces, while the EU initially prioritized a specific technology. What about the third approach? You mentioned China's dual-track concept.
China's strategy is unique because they are applying pressure and incentive at the same time.
How does that work?
On one track, they are constantly tightening fuel consumption standards for traditional combustion engine vehicles. So they're constraining the legacy market, forcing efficiency.
Making the old way harder.
Right. And on the parallel track, they are aggressively promoting new energy vehicles, or NEVs. This synergy is the absolute key to their rapid transition. They're making the old path more difficult and expensive while turbocharging the new path with policy support and massive infrastructure investment.
So we have this embodied AI acting as the operational brain of the car, and carbon neutrality setting the overall strategic direction, even if the paths to get there are different around the world.
That's the framework.
And that convergence, that really sets the stage for the next big topic, which is the car's complete conceptual metamorphosis.
This is where it gets really profound. The conceptual shift is probably the most important part of this whole roadmap. The vehicle is taking on new roles that go far beyond just simple transportation.
It's evolving into this converged terminal you mentioned, integrating energy, high-end computing power, and life services.
Correct. And this shift is vital for anyone listening to grasp. The car's fundamental identity is changing.
So what are the three new identities that the blueprint highlights for this embodied AI?
The three new roles are the distributed energy storage unit, the mobile computing node, and the intelligent living space.
And these three functions are what transform the car from just being an expense into being a multi-use asset.
Precisely.
Okay, let's start with the energy storage unit. This is where the car plugs directly into the grid, right? The V2G functionality.
V2G, or vehicle to grid, yes. This is absolutely central to the whole carbon transition. Because of their large batteries, EVs are inherently mobile storage devices.
And when a car is just sitting idle, which is most of the time.
Which is, according to most estimates, about 95% of the time. The V2G capability allows it to sell its surplus power back to the electrical grid during peak demand times.
So a massive fleet of networked EVs could basically function as a gigantic distributed dynamic power plant.
That's exactly what it is. It turns the car from an energy sink, something you just pour power into an energy asset. It can actively participate in grid regulation, things like peak shaving and frequency modulation.
And that's necessary because of the shift to renewables, right? Solar and wind are intermittent.
They are. So energy stability becomes the key challenge for the grid. A huge V2G fleet provides that necessary regional stabilization.
So you're telling me the stability of a city's power grid in 2040 might literally depend on how many commuters have plugged in their cars after work?
That is the massive strategic implication, yes.
Yeah.
It creates a new revenue stream for the consumer, and it transforms the car into a critical piece of infrastructure.
That's wild. Okay, what's the second identity, the mobile computing node?
Right.
Yep.
So most people think all the chips and sensors in a modern car are just for autonomous driving.
And they're not.
They are. But the roadmap suggests this hardware serves a much larger strategic purpose, processing urban data.
Okay, explain that.
To get to true L4 or L5 autonomous driving, cars have to integrate these incredibly high-end chips and vast sensor arrays, LiDAR, cameras, radar. They basically become mobile supercomputers. And this creates a huge network of distributed compute resources that are essential infrastructure for managing massive amounts of urban data.
What kind of urban data are we talking about here?
Real-time traffic flow, predictive analytics on congestion, weather anomalies, road conditions, pedestrian movements. The vehicles are acting as continuous roving data collectors and processors.
So they're feeding real-time intelligence back into the overall smart city operation.
They're a foundational piece of infrastructure supporting the fusion of the smart city, smart transport, and smart energy, the whole 4S system.
This must be why there's such a strong industry consensus on VRC vehicle road cloud integration.
It is. The car processes data locally, but it relies on the road and the cloud to get the big picture context.
Because the car itself can only see so far.
Exactly. Single vehicle intelligence has physical limitations. The cloud and the roadside sensors act as a kind of sky eye, giving the vehicle intelligence about risks that are outside its line of sight.
Like a car coming around a blind corner.
Or a pedestrian over the crest of a hill. That kind of awareness is absolutely necessary to achieve the safety and efficiency of L4 and L5 driving.
Okay, and that brings us to the third role, the intelligent living space, the so-called third space. This is the big payoff for the consumer, right?
It is, but it's entirely dependent on L4 and L5 automation becoming fully mature.
Because the driver is finally liberated from the task of actually driving.
And when that happens, the entire car interior has to transition. It stops being a driver-centric cockpit and becomes a seamless, flexible third space, a productive extension that bridges your home and your office.
So it's a space designed for work or entertainment or just resting, all while being continuously connected.
It requires a total rethink of automotive design. You're moving from ergonomics for control to ergonomics for productivity and comfort. It's a behavioral and psychological shift as much as it is a technological one.
Right. The value proposition is no longer just moving you quickly, it's about moving you productively. Now, this huge conceptual shift in what a car is must demand a massive restructuring of the industry itself. The roadmap says the traditional chain structure is basically obsolete.
Completely obsolete. That old model parts maker to the OEM to the dealer was rigid, it was transactional, and it was linear.
And it's being replaced by
What the blueprint calls a 3D mesh new ecosystem. It's defined by deep cross-domain fusion.
And this mesh has some core characteristics that define the new competitive landscape. The first one is subject diversification.
Yes, the boundaries have just dissolved. So now, in addition to the traditional car manufacturers, you have these crucial new players.
Like who?
Information and communications technology providers,
Yeah.
the ICT giants, cloud service providers, operating system developers, content operators. These players are essential because the core value of the car is shifting from, metal and oil to software, data, and continuous services.
And the second trait is the shift from transactional relationships to symbiotic partnerships.
Right. The complexity of the challenge means no single company can possibly have all the core competencies. You can't be the best at AI chips and battery chemistry and cloud processing and chassis design all at the same time.
So you have to partner up.
You have to. The relationships are moving beyond simple sales contracts to these complex, interdependent, you and me and your partnerships. Collaboration isn't just a good idea, it's a condition for survival.
Which completely transforms the nature of competition. It's no longer Ford versus Toyota.
Not at all. Competition is entirely redefined as ecosystem versus ecosystem.
I love the analogy they use for this.
It's perfect. An industry expert is quoted as saying, "You are not buying an iPhone, you are buying a ticket to the entire Apple ecosystem."
And it's the same for cars now. Future mobility consumers will be subscribing to an integrated service ecosystem that covers their energy, their transport, and their information needs. The strength of your network becomes your competitive advantage.
It does. And this ambition culminates in the ultimate systemic change that's hinted at in the roadmap. The necessity of moving from a 2D transportation network to a 3D network.
Meaning flying cars?
Meaning integrating air mobility flying cars into this entire smart ecosystem. That's the capstone of this fusion. It promises a generational leap in travel efficiency.
That sounds very long-term. But before we get too far ahead of ourselves, we need to do a reality check. The blueprint actually includes a review of the previous plan, RoadMap 2.0.
It does, and this is crucial. It tells us what foundations have been laid successfully and, maybe more importantly, where the real-world resistance and bottlenecks are.
Right, let's look at the report card.
Looking at the macro environment first, the global auto market is projected to stabilize. Annual sales are expected to stay consistently above 100 million vehicles after 2030. But that stability is a bit deceptive.
How so? It sounds like good news.
Well, the stability hides a massive structural shift in where the growth is coming from.
Okay, so where is the real volume acceleration happening?
The analysis shows a really stark split. Developed markets, the US, Japan, Western Europe, they're mostly engaged in what's called stock competition.
Meaning they're just replacing existing vehicles.
Exactly. The explosive sales volume growth is all coming from emerging markets.
And the big one is India.
India is cited as the core growth engine, with an absolutely astonishing sales growth rate of 77.9% over 5 years.
That is a key strategic nugget right there. It means the future of the car market is going to be overwhelmingly dictated by the preferences and, the infrastructure challenges of markets that are motorizing for the first time, not just ones that are upgrading their fleets.
Exactly. And when we look at electrification, we see how those practical challenges really start to show up.
The global NEV penetration rate is strong, but there's a split in what kind of NEV people are buying.
A critical divergence, yes, between pure battery electric vehicles, BEVs, and plug-in hybrids, PHEVs. And it's all based on region.
Okay, let's run those divergence numbers because this is where market pragmatism really clashes with policy mandates.
So the EU, which is driven by strong policy, shows a clear dominance of BEVs. They hold a 66.1% share of all NEV sales. That's a top-down, regulation-driven outcome.
Okay, now compare that to China, which is the single largest NEV market in the world.
China shows the exact opposite. It's market-driven pragmatism. While BEVs are popular, the PHEV share has rapidly climbed from just 18.3% to a remarkable 40.0% of NEV sales by 2024.
Wow, 40% PHEV. That's a huge strategic tell, isn't it? What does that reveal about the consumer mindset there?
It reflects a very practical consumer demand to solve range and refueling anxiety right now, today.
So they want the flexibility.
They want the electric in the city, fuel on long trips model. In China, especially with the trend toward these larger B-class and C-class vehicles, the PHEV acts as a secure bridge until the charging network is fully mature and ubiquitous.
So if the market had just blindly followed an aggressive pure BEV-only goal, that rapid 40.9% adoption rate might have actually stalled out much earlier. The PHEV is enabling the acceleration.
That's the strategic conclusion, yes. The PHEV is providing the necessary consumer confidence during this messy transition phase.
And the U.S.?
The U.S., meanwhile, maintains a pretty stable 80-20 split between BEVs and PHEVs, which just reflects its more diversified, market-driven approach.
Interesting. Okay, let's talk about the core tech evolution, specifically in battery chemistry. There was a big structural shift in the last RoadMap cycle.
A huge one. There's been a clear industry move away from the high-energy density NMC or ternary cells toward lithium iron phosphate or LFP cells.
And LFP now has over 50% of the market share.
It does.
So this isn't just chemistry jargon. What's the strategic takeaway for the consumer of LFP's dominance?
LFP's strategic advantage is really about cost, safety, and cycle life. It has a lower energy density than NMC, but it's significantly cheaper and inherently safer.
Which makes it the critical enabler for mass-market, affordable electric vehicles.
That's it. And the future roadmap confirms this challenging trajectory. We go from today's liquid electrolyte batteries through safer semi-solid mixtures, and then culminating in the holy grail of high-density, all-solid-state batteries.
And on the autonomous driving front, the blueprint confirms the consensus on two parallel tech tracks.
Right. End-to-end models and vehicle road cloud integration, VRC.
End-to-end is the AI track, right? Raw image in, control command out.
Yes, it bypasses those old manual rule sets, leading to a more human-like, intuitive driving style. And it gets there via that massive data collection from the shadow mode vehicles.
But as we already discussed, VRC is the systemic solution. Just remind our listeners quickly why single vehicle intelligence isn't enough for true L4 or L5 safety.
VRC is the cooperative system. The V is the vehicle with its powerful local intelligence. The R is the road, which provides external sensors, smart traffic lights, cameras that see beyond the vehicle's line of sight. That sky-eye intelligence we talked about.
And
The C is the cloud, which processes all this massive data and optimizes the system's behavior globally. Without VRC, a vehicle just can't safely navigate complex urban environments because it is physically blind to critical external risks.
it provides the necessary situational awareness.
It does.
Okay, so let's turn to the official report card for that prior strategy, RoadMap 2.0. The narrative seems to be one of massive success, but with some critical structural failures. Let's start with the wins, the super expected achievements.
The clearest winner, by far, is NEV penetration. The 2025 target was actually pretty conservative. They were aiming for 15% to 25% penetration.
And where did they land?
By 2024, the actual figure had already reached a phenomenal 40.9%. This is an acceleration in market adoption that just dramatically exceeded all the initial projections.
And the intelligence targets for things like L2 driver assist?
Intelligent connectivity met expectations, reaching 57.3% penetration. And on the powertrain side, the industry actually surpassed its efficiency goals. Dedicated hybrid engine thermal efficiency hit 46.5% by 2024, which already beats the 2025 goal of 42 to 44%.
So, tremendous success in market uptake and the efficiency of hybrid engines. Where did the plan fall short? What were the crucial areas facing challenges?
The gaps were really concentrated in areas related to the legacy market and some prevailing consumer trends. Fuel efficiency for traditional passenger vehicles missed its 2025 target.
What was the target and what was the result?
The target was 5.6 liters per 100 kilometers. They only got to 5.9.
Why the miss? If the tech existed for 46% thermal efficiency in hybrids, why couldn't the overall fleet meet its efficiency target?
The source points to two critical factors that basically counteracted all the technological gains. First, the trend toward larger vehicles. B-Class and C-Class cars now exceed 40% of the market share globally. Heavier cars just need more energy.
Okay, and the second factor?
Low HEV penetration. So the segment that was specifically designed to maximize internal combustion efficiency was only 2.7% of the market. The efficiency gains were there in the technology, but consumer preference for bigger, more feature-rich vehicles completely offset them.
So, consumer choice for size and luxury effectively slowed down the rate of carbon reduction in the legacy fleet. What was the second major miss?
Lightweighting. The plan was aiming for a 10% reduction in the vehicle lightweighting coefficient. The industry only achieved a 7.5% reduction for traditional vehicles.
And that's connected to the bigger cars trend as well.
Directly linked. It's because of the trend toward larger vehicles, increased safety requirements, especially for passive safety, and all the added weight from the electronic and comfort features you need for these new intelligent terminals.
This whole report card gives us a really clear picture. Explosive wins in the new transition technologies like NEVs and hybrid engines, but this structural resistance from consumer trends and the legacy tech pathways.
And that brings us to the four massive systemic hurdles that the industry now has to overcome. This is what the blueprint calls the deep water stage of transformation.
Okay, let's lay them out. What's the first one?
Number one is core technology gaps, or the choke points. The foundational technology accumulation is just not sufficient yet.
What kind of tech are we talking about?
We lack proprietary solutions in critical areas. Things like solving the low-temperature performance issues for batteries, developing our own vehicle operating systems so we're not dependent on external providers, and securing a supply of high-performance automotive-grade chips. These are the supply chain choke points.
Okay, bottleneck number two.
Lack of cross-industry collaboration. The future absolutely demands this deep fusion between automotive, energy, and communication sectors. But there's still massive barriers.
Like what?
Technical standards, data interfaces, security boundaries, the necessary stable, efficient, cross-industry cooperation frameworks, and crucially, the viable business models for things like VTG operators or cloud providers. They just don't exist yet.
Number three.
Verification and standards lag. Technology is just iterating at a speed that governance and our testing infrastructure cannot keep up with. The clearest example is L3 and above autonomous driving. The required coverage of public road test scenarios is still less than 50%.
Which makes large-scale, safe deployment incredibly risky.
Very risky. And key VRC standard frameworks still have significant blanks that need to be filled in before a mass rollout can happen seamlessly across different regions.
And the final bottleneck.
Talent structure imbalance. This shift is causing a dramatic structural dislocation in the workforce. Demand for traditional engineers, like combustion engine experts, is rapidly contracting.
While the demand for new skills, AI, software architecture, fuel cells, is huge and unmet.
Exactly. And our educational systems are lagging severely in preparing this new software and data-centric workforce.
You know, that second point feels like the most strategic challenge. A breakthrough in battery density is kind of meaningless if the grid, the energy partner, isn't ready to handle the load and the bidirectional flow.
That's the core thesis of this deep water stage. The bottlenecks are systemic and they're interdependent. You can't solve the future with a past mindset of siloed industrial development.
That reality check is a necessary foundation. Let's transition now to the most forward-looking part of this analysis, the 2040 blueprint itself. What's the grand vision?
The overarching goal is to build an innovative, data-driven, resilient, and sustainable modern automotive industry cluster by 2040.
And the targets are, well, incredibly ambitious. They really define what success for those two engines of change would look like. Let's detail those four specific high-stakes targets.
Okay, first, carbon emissions. The industry aims to hit its carbon emissions peak around 2028.
2028, that is an extremely aggressive timeline.
It is. And after that peak, they're targeting a dramatic drop of over 60% from that peak by the year 2040.
Okay, target two.
Market structure. New energy vehicle, or NEV, penetration must exceed 80%, establishing it as the absolute market mainstream. Traditional fuel vehicles will become a niche product.
Third.
Intelligence. We need to see mass application of high-level autonomous driving L4 and L5, and that has to be underpinned by a fully mature and operational VRC ecosystem.
And finally, the fourth target.
Global status. The goal is to fundamentally shift the global balance of power, making the industry a global source of original automotive technology innovation.
So let's dive into the phased milestones. The checkpoints for 2030, 2035, and 2040. Starting with market penetration for passenger cars, we saw that current consumer preference is for PHEVs as a pragmatic bridge. How does the roadmap see that changing over time?
It predicts a gradual strategic phase-out of that PHEV bridge, moving decisively toward pure BEV dominance.
Okay, give us the numbers.
For 2030, NEV penetration is expected to reach about 70% of new sales. And importantly, the BEV to PHEV split is projected to be 50-50.
So a 5.5 split, that acknowledges that range anxiety is still a huge issue.
It does. Then by 2035, NEV penetration goes up to over 80%. The split shifts to 6.4 in favor of BEVs. Pure electric starts to dominate.
And by 2040?
By 2040, NEV penetration is over 85%, and the split is heavily weighted toward pure electric, 8.2 BEV to PHEV.
That 2030 target, that 50-50 split, that feels like a strategic recognition that if you force the pace too quickly on pure BEVs before the infrastructure is totally ready, you'll risk a consumer backlash.
And you'd slow down that 80% penetration goal. It's a pragmatic, market-driven strategy for the first decade. It allows the charging infrastructure and the battery tech time to catch up.
What about the penetration targets for autonomous driving? For L3 and L4 functionality?
The trajectory there is very steep, and it relies heavily on that safety leap we talked about.
So what are the numbers?
By 2030, L3, L4 functionality is expected in over 35% of smart connected vehicles.
And then a big jump by 2035.
A huge jump to over 70% penetration by 2035. And then by 2040, L4 is fully widespread and mass applied in defined environments, with L5 the ability to drive anywhere, anytime, starting to enter the market.
Now for the battery targets. This is central to the energy revolution and frankly a massive material science challenge. These targets are for the high density route, right? For long range and premium vehicles.
They are, and these milestones require the commercialization of the next generation of battery technology.
So the goals.
By 2030, mass energy density has to reach or exceed 500 watt-hours per kilogram.
Yep.
By 2035, that increases to over 600. And by 2040, the ultimate goal is over 700 watt-hours per kilogram.
And just for perspective, that's roughly triple the density of many of the current mass market LFP cells.
It is. It requires the successful transition to all solid state, or at least advanced semi-solid batteries, and solving some major thermal management and reliability issues along the way.
Finally, let's revisit the ultimate vision of ecosystem fusion. The roadmap has specific goals that define the transition to a wholly interconnected 3D transport network.
The targets here really demonstrate the scale of the systemic overhaul that's required. By 2030, highway charging stations need to become widely popularized. That's a key infrastructure enabler.
Then what?
By 2035, smart highway coverage, meaning VRC functionality, is enabled, has to reach 50% of the entire network.
And by 2040, this is where the really disruptive marker comes in.
It is. Flying cars achieve mass application scenarios. The target is to have over 100,000 units in operation.
100,000 flying cars.
This is a deliberate, strategic goal to shift the mobility paradigm from a two-dimensional surface-bound system to a three-dimensional transportation network.
100,000 flying cars in operation within 16 years. That is a breathtaking ambition. It fundamentally shifts the investment focus from just optimizing the roads we have to creating entirely new parallel infrastructure and services.
It confirms that the transformation being planned is not about optimization. It's about the creation of a new, parallel mobility structure.
So to achieve this grand vision, the blueprint relies on what it calls the 1 plus 5 plus X technical architecture.
That's right. It's one general roadmap, 5 core technology clusters, and X number of focused topics.
We need to examine the concrete metrics for those 5 core pillars, but let's focus on the strategic implication of these numbers, not just, reciting engineering specs.
Agreed. Let's start with the first and most foundational cluster, the energy saving and new energy technology cluster. This is where that carbon neutrality engine meets materials and powertrain engineering.
What's the vision here?
The vision is all about diversified power sources. So, hydrogen, synthetic fuels, and advanced traditional engines, all optimized by intelligent energy management.
Let's group the powertrain efficiency metrics together. What's the strategic message about the internal combustion engine in 2040? Is it dead?
The message is that it won't disappear completely, but it will be relegated to high-efficiency hybrid use. Peak thermal efficiency for dedicated hybrid engines is targeted to reach an astonishing 48% by 2040.
Up from 45% in 2030.
Correct. This ensures that even the legacy part of the system is contributing as much as possible to the carbon reduction goals.
And the battery story. We know the high-density target is over 700 wh/gram, which requires all solid state. But what about the mass market, affordable route?
The roadmap strategically differentiates 2 battery paths. The high-density route is for premium, long-range performance. The mass-market cost-effective route, which is what will dominate the volume targets, a lower but safer and more affordable number. Over 350 wh/grams by 2040.
So that confirms a commitment to both performance and affordability.
It does.
What about fuel cells? They seem crucial for heavy commercial vehicles where batteries are just impractical due to weight and charging time.
Right. For passenger car fuel cell stacks, the power density has to reach or exceed 9.0 kilowatts per liter by 2040. That's necessary to make hydrogen systems compact enough for mass adoption.
And for the big trucks.
For heavy trucks, around 49 tons, fuel efficiency is the critical metric. Hydrogen consumption has to drop below 6 kilograms per 100 kilometers by 2040. That efficiency leap is what will enable hydrogen to compete economically with diesel and freight transport.
Okay, let's move on to the cluster that enables that embodied AI, the Intelligent Connectivity Technology Cluster. The vision here is really specific. Autonomous driving capability must fully surpass professional drivers in safety, adaptability, and efficiency.
And that has to be proven with data.
Right.
This vision is backed by probably the most challenging safety metrics in the entire blueprint. It's about the reliability of L3 automated systems before L4 becomes mainstream. The key measure is the L3 intervention rate on highways.
Measured per 10,000 kilometers.
Yes. And the leap in reliability we're tracking here is huge.
What's the target?
In 2030, the intervention target is 3 or fewer times per 10,000 kilometers, meaning 3 human takeovers are expected. By 2035, that has to drop by 90% to 0.3 times or fewer.
A 90% reduction in just 5 years.
That 90% reduction between 2030 and 2035 is not a marginal gain. That is the strategic moment when the computer officially becomes statistically more reliable than the human driver. It signals that we're ready for L4.
And the ultimate safety measure accident frequency has to follow that reliability curve.
Absolutely. The accident interval mileage target for highways has to increase tenfold, from 1 million kilometers per accident in 2030 to 10 million kilometers per accident by 2040.
And that level of safety is only possible with that fully deployed VRC infrastructure.
Only.
So let's focus on that VRC build-out, the smart infrastructure targets.
His deployment plan is massive. In 2030, VRC will cover key cities and about 20% of major highways. By 2035, it expands to cover all third-tier cities and 50% of highways.
And by 2040.
By 2040, VRC covers all county-level cities and 70% of highways. And the precision of the network, how accurately the system knows where every moving part is targeted to be 20 centimeters or less by 2035.
That centimeter-level accuracy is what you need for that kind of coordination between vehicles and infrastructure at high speed.
It is.
Okay, now the foundational layer, the common supporting technology cluster. This underpins everything: chips, chassis, software. If these fail, the L4 and flying car targets are just impossible.
This cluster is all about building those foundational capabilities. The EE, or electronic architecture evolution, is key here.
So how does the computational architecture of the car actually evolve?
The goal is to move from today's fragmented systems toward radical centralization. 2030 will see the implementation of a central computing plus zone architecture.
And by 2040?
By 2040, the goal is a fully centralized vehicle cloud architecture. The car will act primarily as an execution terminal, and the massive computational tasks like AI model updates and complex planning will be handled elastically in the cloud.
And the chip requirements to support that.
The automotive chips have to evolve incredibly fast. They need to support L4 functionality by 2030, L5 by 2035, and the 2040 vision requires chips that enable a transition from universal AI to super AI. One-chip solutions will become mainstream.
So highly integrated multi-domain chips that handle everything from driving to the cockpit.
Exactly, and the vehicle operating systems, the OS, has to achieve full-stack technology capability and widespread industrial application by 2040. This is really a race for proprietary, secure, and updatable software platforms.
And finally, the smart chassis. This component has to be ready to support not just ground transport, but these radical new vehicle forms.
Yes, by 2040, the industry is aiming for a major generational change towards split-body reconfigurable designs.
What does that mean?
It means a chassis in the cabin might be designed to separate or reconfigure, enabling extremely agile X, Y, and Z-axis collaborative control. This kind of flexibility is essential for entirely new vehicle forms, like those capable of vertical takeoff and landing, or even diagonal movement in tight spaces.
That split body design is a fundamental break from 100 years of automotive tradition. It sounds like the engineering strategy is actively preparing for 3D mobility.
It connects directly to that final convergence cluster,
Hmm.
the cross-industry deep fusion metrics. This defines the scale of the trillion-dollar ecosystem that's being built.
Let's focus on automotive and energy, the V2G and hydrogen goals. How integrated will the car be with the grid?
The integration targets are incredibly aggressive. By 2040, V2G terminals, charging piles capable of bidirectional energy flow, must account for an astonishing 80% of all new charging piles being installed.
80%. That mandates that the new charging infrastructure is overwhelmingly designed to be a grid management tool.
And it means we absolutely must solve that cooperation bottleneck between the utility companies and the auto sector in the next 15 years.
Right.
Furthermore, the goal is to construct a large-scale hydrogen infrastructure, 10,000 to 20,000 hydrogen fueling stations built by 2040 to support that heavy commercial vehicle transition.
And finally, the ultimate fusion target, automotive and transportation, the 3D shift. This is the payoff for all those chips, all that software, and those reconfigurable chassis designs.
By 2040, the roadmap is targeting 100% smart intersection coverage in all county-level cities and above. And the most futuristic metric confirms that 3D mobility shift.
The flying cars.
The flying car fleet size is targeted to exceed 100,000 units in operation. It will achieve mass civilian and commuter scenarios with an impressive aerial range of over 9,000 kilometers.
That 1,000-kilometer aerial range, that's not just for local air taxis. That suggests intercity or even regional travel is being anticipated through these 3D networks.
It is.
So we've covered the drivers, the reality checks, and the final technical requirements for this generational blueprint. Let's try to summarize this.
In conclusion, this blueprint really confirms that the automotive world is navigating a true ecological revolution. It's being driven relentlessly by AI and that mandate for carbon neutrality.
And the core opportunity for any business listening is strategic. Value is fundamentally shifting away from traditional manufacturing.
That's right. The maximum value creation is no longer going to be found in one-time hardware sales. It's shifting to continuous service revenue that's derived from the vehicle's three new roles.
As an energy asset, a computing mode, and a service platform.
Exactly. The vehicle is simply the access point, the gateway to a multi-trillion-dollar ecosystem.
But the analysis also gives us a pretty sober warning about the systemic nature of the challenges we reviewed.
The bottlenecks, the talent gaps, the standards lag, the foundational tech deficits, they are fundamentally systemic. A single-point technological breakthrough is almost rendered moot if the grid infrastructure, the data standards, and the talent pipeline don't evolve concurrently and cooperatively.
Which requires unprecedented levels of public-private and cross-industry cooperation.
Something the industry has, historically, really struggled with.
Which means the old model of competition is entirely obsolete.
Completely. Competition has irrevocably transformed from brand versus brand to ecosystem versus ecosystem. Isolation is a strategy for obsolescence in the 2040 context. The new currency of success isn't just market share. It's the strength, the breadth, and crucially, the interoperability of your partnership network.
So the technology blueprint promises this future of incredible safety, efficiency, and convenience. We see it in the L4 proliferation, the shift to 3D transport, the cognitive intelligence of the cabin. But there is one final provocative thought that we should take from this, moving beyond the technology and into the ethical boundary.
Hmm.
When the vehicle transforms from just a passive tool into an active cognitive partner, a system that inherently knows our schedule, our traffic expectations, and eventually our preferences, maybe better than we know ourselves, what are we giving up besides just control of the steering wheel?
That's the question. What is the cost of absolute convenience when the machine starts making decisions on your behalf?
That is the essential boundary we have to contemplate as we accelerate toward this embodied AI future. The trade off between seamless convenience and our own human autonomy. Something for you to chew on as you wait for your next vehicle to proactively send that email for you.